So in this video, we will try to make sure everyone's aware of how to go from this differential equation that you see listed here to its general solution, which you see listed here. A few sneaky things happen in this derivation, and I think it's probably worth putting this video together to try to discuss what they are. So let's go ahead and talk about where this differential equation arises from in the first place. So if you make this assumption, the rate at which a quantity changes is directly proportional to the current level of the quantity, that arises in this differential equation. Keep in mind, a derivative y prime with respect to time is a rate of change over time. So if a rate of change is something else in math, it's equal to it. So the rate of change is proportional, meaning there's some constant of proportionality represented by this constant k that we multiply the current level of the quantity by. If y prime is the rate of change of the quantity, the current level of the quantity is going to be given by the function value y of t. Where would you ever use this? Why is what we're talking about within this video significant? So this assumption, I'm thinking you're going to realize, makes sense. The rate at which a population changes is directly proportional to the current level of the population. If the population's high, there are more members of the population to reproduce to make the population grow more quickly. If the population's low, it's not going to be growing as quickly, right? The rate at which the population changes is directly proportional to the current level of the population. If you invest a bunch of money in the stock market and you're just going to let it sit there for 40 years, the rate at which that investment grows is directly proportional to the current value of the investment. If it's growing by a certain percentage each year, it's going to compound more quickly after it's been growing for 30 years rather than after it's been growing for 1 year. The value of that investment will be much higher. It'll be earning much more quickly after a long time frame. This last one here is going to be involving decay. This differential equation models both growth and decay. We'll talk about why after we read this. The rate at which a radioactive substance decays is directly proportional to the current amount of the substance. So you have 100 grams of a radioactive substance. It has just started to decay. If the half-life of that substance is 1 year, it's going to lose 50 grams over that first year. It's going to be decaying more quickly across that first year than it is across the second year, because think about what's going to happen. If there's 50 grams at the start of that next year, it's only going to decay 25 grams over the course of that year. So the amount that is decaying per year is obviously decreasing over time as less and less of the substance remains, which is why it's a fair assumption to make right here. The rate at which it decays is directly proportional to the current amount that we have. So how does this model decay? Well, if k is negative and y of t is positive, and we'll talk about why y of t is in general going to be positive in a few minutes, then your growth function changes to a decay function. If a derivative is negative, your rate of change is negative, your quantity is decreasing. So if k is negative, this models decay. If k is positive, this models growth. So how do you get from the differential equation to its general solution? So I have the differential equation that you've seen across the last few screens copied again at the top of this one. Now, for this particular differential equation, we're going to use the method of separation of variables in order to develop the general solution to it. It's just more convenient to use Leibniz notation whenever you use separation of variables. Leibniz notation kind of works well with the typical rules of algebra, which is why it's more convenient. So to separate the variables, I'm basically going to be multiplying both sides of my differential equation here by dt to get the dt separated from the dy, but then I also want to move any y's that are on the right side of the equation over to the left side, so I would divide both sides by y. So this first step that you see in just the blue is the separation of variables step. Once your variables are successfully separated, which again means the dy and any y's are on one side of the equation and the dt and any t's are on the other side of the equation, you're going to take the antiderivative of both sides of the equation. Now, when you take the antiderivative on the left side here, you can think of this as 1 over y with respect to y. You're going to end up with natural log of the absolute value of y. The antiderivative on this side is a little bit weird. K is a constant. You're not doing this antiderivative with respect to t, so you're not going to add 1 to the constant and then divide the constant by by the new exponent of 2, you're not applying the power rule to k, you're applying the power rule to t. There's really a t to the 0 right here. So if I apply the power rule to that, I'm going to get this constant copied in, k copies in. I'm going to add 1 to the power of 0 on the t, so that's t to the first. Don't have to show the first power, don't have to show the division by 1 either. So I do have a plus c on this side. If you're wondering why there's not a plus c on this side, it's because what we want to do is we want to turn around and try to isolate the dependent variable at the conclusion of this. The dependent variable is y. Y depends on t. So if I add a constant on this side and I add another constant on this side, but then I algebraically try to solve this equation for y, I'm going to be combining both constants on this side of the equation, and the combination of two unknown constants just arises in a third unknown constant. So it's just common practice to leave the constant of integration only on the right side of the equation, which is where your independent variable is typically going to lie. Either t or, in other cases, x would be the most frequently used independent variables. Now, how do I go through the algebraic process to isolate y? Well, I'm going to have to get the absolute value of y out of this natural logarithm function. And so I'm going to use a step called exponentiation, which basically means both sides of this equation become exponents on a base e. Now, when I do that on the left, the natural exponential and the natural logarithm are going to undo each other. They are inverse functions. So I'm just left with what was inside that logarithm, which is the absolute value of y. On the other side, I'm going to have e raised to kt plus c. This is the point in the process where I see students have a little bit of an issue with what happens next. And it is weird, but I think as we talk through this, you're going to realize why this sequence is going to be okay and actually quite convenient for us to carry out. If you think about e to a power, I have a graph of e to the x right here. The graph of e to the x, no matter what ends up in this power, negatives end up in the power, 0 ends up in the power, positives end up in the power. The graph of e to the x is always positive. E to a power, no matter what ends up in the power, is always positive. That's why on the left side of this equation right here, I've maintained use of absolute values around that y. Now we do want to find a way to get rid of the absolute values. One way to do that would be to re-express this as a piecewise function, which is not incorrect, but there's actually a somewhat sneaky, more convenient method for us to use. And here's what I notice about the right side of this equation. I see addition in the exponent. When do we add exponents together? We add exponents to one another when we have multiplication of like bases. So I'm guessing over the time you've spent studying math, you've seen expressions like this. E to a power times e to a power. Oh, I can simplify that by writing e to whatever was in the first power plus whatever was in the second power. We're just kind of going the opposite way down that street right now. We're breaking up the addition in an exponent into multiplication of like bases. And if you notice this expression right here, if c is a constant, e is also a constant, 2.7-ish. 2.7-ish, that irrational value e, raised to a number, is just going to be some other number. What I've highlighted right here on this line is some number. Now, I don't know the value of that number, but what I'm going to do is I'm going to re-represent that number with an arbitrary constant a. And it's important to say that it's arbitrary, because if I say that a is equal to e to the c, I have to maintain use of the absolute values, because e to the c is only ever going to be positive. But if I find a way to allow the right side of this equation to become negative, I can then drop the absolute values around the y, because then that side of the equation can also become negative. So if I do not demand that a is equal to e to the c, if I just say a is going to be an arbitrary constant that is being used to re-represent this, and I allow for a to become negative, once I've given the right side of this equation a way to become negative, I can do the same thing on the left side of the equation, and I can drop the absolute values. So this is called the general solution to the differential equation. If you Google for some exponential growth, decay, story problems, you'll definitely see how to use this general solution. But in this video, we wanted to take time to talk about this derivation, particularly this little progression from something that could only be positive on this side to something that can now be negative through the use of that arbitrary constant a.